Going live. Okay, I don't know why it's taking so long. You're live now. Okay, just take 1 second. Hang on a second. Let me share the screen. Going live. Okay, I don't know why you're live now. Good. So you see the screen here. So, okay, let me start. So welcome everybody to the online SPICE on SPIN+X online meeting. We have, as usually, this is a seminar series organized by Spin Phenomena Interdisciplinary Center and the Collaborative Research Center of SPIN+X. Led in Kaiserslautern by Martin Schliemann and Burkhard Hillebrands, and by Matthias Klaue in Mainz. And of course, the SPICE Center is organized by myself, Hariom and Karen now in Duisburg. As you know, this is a Zoom live streaming seminar series, a Zoom webinar format, meaning that please write a Q&A on directly or raise your hand, and I will promote you to panelists to ask the questions to the speaker. So if they are very important, we can do it during the talk, but mostly at the end of the talk, the Q&A, and particularly today, Karen will administer that. And please check out the next talks that we have. We have at the end of the year talks, and then we will continue on, including until February or March next year as well. Now, just a quick introduction to the speaker today. Hariom Jani is a Senior Research Fellow, Department of Physics at the National University of Singapore, and is one of the young research leaders of our field. We had the pleasure of listening to some of his talks previously in one of the conferences, and I was very impressed and wanted to invite him to this series, and so he could share his physics with you on quantum materials, topological spin textures, and antiferromagnetic spintronics. And outside electronics. So with that, I will stop sharing. I will ask Hariom to go ahead and share your screen and start whenever you like.
Is that clear?
Yeah, we can see it. Perfect.
Okay. All right. So I would firstly like to thank Hariom and the entire SPICE team for inviting me for this opportunity. I feel extremely honored and privileged to be a member speaking here. And the focus of my discussion today centers on the observation and the control of topological textures in antiferromagnetic systems. I would firstly like to address the Skermionics part, and then we go to antiferromagnets. Firstly, Skermions is something that is very well understood in this community, and we know these to be whirling topological textures, which consist of winding in a very specific and a unique sense. I have shown a very simple structure here, which consists of a mapping from a hedgehog, kind of a three-dimensional object, onto a flat structure, which we know very well as the nail Skermion. In thin films, this would be realized actually as some form of a tube, where the structure is maintained along the z-axis, but then the spins wind in the xy plane in a specific manner. And therefore, it is possible to define a topologically non-trivial entity called the topological charge, which is obtained by performing a very simple integration of the solid angle spanned by the local spins. It's arranged such that the overall solid angle for a sphere would add up to 4 pi, and that would be wrapping a unit sphere, and therefore wrapping the hemisphere would constitute half a topological charge. I would like to spend a little time on sort of unwinding some of these objects, and then we'll see them much more closely as we look at the experimental results. So we start off firstly with the nail Skermion, which we know is topological charge 1, and we can obtain an entire topological zoo from a very simple structure like this, starting firstly from the nail to the block Skermion by adding a change of helicity, or by completely changing it into what is called the anti-Skermion, which is obtained by changing the winding direction. This really is a mixed chiral topological object because it consists of both chiralities, including nail and block structures, depending on which sectors you look at. And so the object is structured that way. If the cores are aligned, this tends to have an opposite value of topological charge because of the change in the winding sets. Now, we can go from skermions to merons by basically only mapping half the unit sphere, and you can also obviously gain the antimeron, which is also obtained in a similar manner from the anti-skermion. But the more exotic structures, which are just emerging to gain attention, are those constructed from multiple pairs of these objects. So for example, if we take a meron and antimeron with both their cores aligned, as you can see, their topological charge is +½ and -½ they would actually constitute to form a trivial pair as shown here. If, however, we actually have a meron up, antimeron down, for example, then we have +½ -½ and that would actually constitute a topologically non-trivial object, which is called a nail bimeron. Various other combinations can also be achieved, and you can also have Q = 1 or -1, depending on how these permutation combinations are realized. Now, an interesting feature of the nail bimeron is that, of course, you can also obtain this from the skermion by simply actually rotating the spins, and therefore the key difference between the textures below versus above is the background in which they exist. The top ones exist in an out-of-plane background, whereas the ones below exist in an in-plane background, and therefore, depending on the material symmetry that we look at, they would appear in different contexts. Now, we know why skermionics are important, primarily because they can be used as variants of chiral domain walls, which have been extremely well studied in the spin-X community, to construct racetracks. It is also possible now to use them to construct logic because of their quasi-particle nature. There are excellent investigations theoretically in this direction, and very nice work also of looking at alternative computing methodologies, both neuromorphic and reservoir computing, particularly by the Mainz group here. Now, that said, there are some fundamental drawbacks of using purely ferromagnetic textures that I would like to quickly highlight, which is firstly that they are susceptible very strongly to external magnetic fields. Not always, but often they require the presence of fields for their stabilization. They exhibit the Skermion Hall effect, which is a transverse deflection of the object when driven by currents because of gyromagnetic torques, and also the presence of long-range internal dipolar fields restricts how small the textures can be made, therefore prompting us to look at alternative ways to realize topological textures, and that has really brought in a strong attention to antiferromagnetic community. Now, antiferromagnets, as the name suggests, and is also very well known in this community, is consisting of more than one magnetic sublattice, which usually would add up in a way such that they cancel off each other overall, and therefore the order parameter used to define antiferromagnets is the nail vector, which is in the simplest sense constructed by subtracting maybe two magnetic sublattices, or in more complex cases this can be much more involved. But the crucial feature that they hold is because of their effectively cancelled out sublattices from far away, they effectively behave like non-magnetic objects. They are not influenced by stray fields, although they actually have very robust internal order. They exhibit ultra-fast dynamics, which has really brought the attention of the spintronics community to these materials, which for a long time were not given significant attention to because they were very difficult to study and manipulate. Now, given the context of antiferromagnets, marrying skermionics with antiferromagnetism would then bring some unique advantages, addressing the limitations that I already mentioned above. And this was emerging very strongly from the hallmark theoretical proposals by Joe Barker and team, as well as the Ezawa groups, where they very clearly illustrated that it's possible to achieve topological textures which do not undergo transverse deflections, and they're very robust against external perturbations. In fact, these topological objects can move at ultra-fast speeds, and that is a novel addition. This was not only investigated in these works, but also some important works. And the key feature to note here that I would like to draw your attention to is that the speed of topological textures scales with, of course, the current density, but is inversely proportional to the Gilbert damping constant. And therefore, this allows us some very interesting opportunities to achieve ultrafast physics. This is not only for Skermions as shown here, but also for textures such as bimerons, which I've illustrated before. And these also exhibit ultrafast dynamics. To a certain extent, this investigation was realized, at least the stabilization part and the absence of Skermion Hall effect in synthetically coupled ferromagnetic layers. And these do seem to be promising. However, because synthetic AFM systems are coupled by the RKKY interaction, often the extreme limit to which they can operate is limited by the strength of the RKKY coupling, and beyond a certain limit, it would break down. So the interest is obviously always to go to natural antiferromagnetic systems and see if we can realize the body of Skermionics in those materials. This is not an easy task because they have very robust orders, and studying the Néel vector by itself and mapping it out at the nanoscale is not a trivial problem. So today I'll be sharing some of our results in this direction and discussing with you the experimental techniques and the scientific ideas underlying these developments that we've just made. So first and foremost, I would like to draw your attention to the Kibble-Zurek mechanism, which is really central to our development so far. And this idea comes from almost 50 years ago, proposal by Kibble for cosmological physics, where he suggested how one might be able to stabilize topological strings in the universal context. But we realize that this actually has some very interesting consequences for condensed matter systems as well. So the idea involves the use of a system which starts from a disordered state, and as it undergoes a phase transition into the ordering regime, that emerges pockets of order. Evidently, these would not be coupled to each other because they would be space-like separated for the order parameter communicating between them, and therefore they would be not aligned with respect to each other. When sufficiently below the transition, these domains would expand, and we would land up getting textures such that they have some kind of domain walls in the middle. Often this would be resulting in trivial kind of domain walls, but probabilistically it would necessitate that the textures of the domain orientations emerge in very special configurations to stabilize topological objects. So one example is that of a Mexican hat potential. So if we were to have the energy ground state as a ring, mathematically symbolized by the U1 symmetry, and all the magnetic orientation is along the basal orientation, it may be possible to actually trap a topological defect in the center, which is energetically unfavorable, as shown in this case here. This was originally proposed in liquid helium and eventually observed in liquid crystals, BECs, multiferroics over the last many decades. And we wondered if this can actually be translated to antiferromagnets for us to create topological objects in them. And it turns out that this is possible. So before going into the technical nuances, I would like to sort of iterate what are the key material requirements. So first and foremost, we want the system to be antiferromagnetic or significantly made up of significantly compensated sublattices, which would allow us to make the system robust and weaken dipolar interactions. It should have an easy plane anisotropy, which would favor U1-like symmetry. This is, one of the conditions. There could be other ways of realizing the symmetry as well, but we felt that this was something easier to achieve, for example, in an axial system. It is then important to actually have access to a phase transition to then perform the Kibble-Zurek quench. It would be beneficial to have low Gilbert damping. So once we obtain topological textures, they can be driven at ultrafast speeds. It's also interesting to look at systems which host coupled degrees of freedom. This we will look at particularly in some cases that I will discuss later on, so that it enables tunability, which could be non-volatile in nature. And of course, it's important to actually have current-driven motion of textures, so there has to be some ability to inject spin torques. Now, the system that we think is a good one to address these needs is a heterostructure of Fe2O3 with some other layers, but primarily the main functional layer is Fe2O3. This is because it consists of weakly canted antiferromagnetism it has a room temperature state exhibiting effectively U1 symmetry. It is not exactly U1 because it actually has a 6-4 structure, but because the basal anisotropy is really weak, we can effectively call it U1-like. It has access to both Néel and Morin transition. There is a very nice body of work done in Mainz, which actually shows that the Gilbert damping in the system is ultra low, making it really promising for ultra-fast dynamics. It is also known to host spin-charge lattice couplings, and it is possible for us to exploit PT overlayers to actually inject spin currents in the system. Now, the interesting feature about alpha Fe2O3 or hematite is that it is also the main component of rust. And as a consequence, it is actually earth abundant and making it very cost effective to resource. So with that basic introduction, I would first like to convince you how the Kibble-Zurek mechanism works in the case of Fe2O3, and then we look at the experimental data. So some of the results shown here are by my colleague Jia, and we have actually used atomistic simulations appropriately and accounting for various atom-atom exchanges in the system, and this is done in this code called Vampire. Shown here now is beginning from the state of the paramagnetic behavior, and we are showing just the topmost layer of the antiferromagnet, and let's see what actually happens. So as you can see here, originally it's completely disordered, and as the system undergoes the phase transition, we actually start to see emergence of magnetic order until we evolve the system and we observe a rich mosaic of variation of the textures. Predominant background is, of course, in the plane because it actually has the easy plane state in the configurations that we're looking at. And there is still some presence of out-of-plane orientations, which really corresponds to the textures that I had shown in the beginning. Some consisting of out-of-plane cores, which could be mirrons or antimirrons of different orientations that are blue, and some of them are actually even pairs, as seen in some of these configurations, which could either be bimirrons or topologically trivial pairs, which we will look at subsequently. So having convinced that it is possible to realize Kibble-Zurek transitions in system with appropriately monitored A and K parameters corresponding to exchange and anisotropy, let's actually look at what happens in the system and how do we do it experimentally. So the ground state, the free energy of the system can be described by the following important terms here. Firstly, the exchange which guides the paramagnetic to antiferromagnetic phase transition. It has a very high Néel ordering temperature at about 960 Kelvin. Of course, this is extremely high, and it orders into the in-plane antiferromagnetic state. There is also a bulk homogeneous Delezinski-Moria interaction with a D vector out of plane, which causes an in-plane canting of the magnetization, which also lands up giving some kind of macroscopic moment that we can measure at room temperature. The last ingredient is the magnetocrystalline anisotropy, at least the dominant interaction, which is then given by an axial interaction emerging from very delicate competition between magnetic dipolar and single ion. So as I mentioned, long-range dipolar fields may still be absent in the system, but local magnetic dipolar interactions actually enforce some form of anisotropy, which favors in-plane interaction. And as expected, this would be the expectation value of the Z component squared for the spin. And then the single ion interaction comes from the very weak spin-orbit coupling in the system. It's weak because the Fe2O3 consists of Fe3+ ions, which are almost spherically symmetric, but the deviations from the spherical symmetry allows us to have some kind of spin-orbit coupling, which then gives us single ion anisotropy favoring out-of-plane direction. So the competition between them as a function of temperature then allows us to have very rich transitions at room temperature. This is an easy plane system, which can actually give the overall macroscopic moment, but at low temperature, this becomes an easy axis phase because of the dominance of single ion with respect to magnetic dipolar. And as soon as M becomes parallel to D, of course, the canting vanishes and therefore the signal would also vanish. So this is all very well understood. Now, experimentally speaking, if we want to do Kibble-Zurek quenches, the ideal way to do that would be to use the Néel transition, which is actually what was proposed, a second order phase transition. But this is experimentally very difficult to do. And by the time you actually take realistic samples to those temperatures, you start to lose oxygen vacancies in vacuum environments. And therefore, it is actually much more preferable to use the other phase transition in the system, which is also called as a Morin transition. And to convince you that this is actually going to work, the key point to note is that because of the easy axis phase, it is in fact some sense topologically trivial because it only has the two ends of the unit sphere available to itself, whereas the easy plane phase is topologically rich, exhibiting effectively U1-like symmetry because of the fact that the basal anisotropy is weak. Now, let's look at some experimental techniques that we have investigated. A good body of work that allowed us to make this progress was actually with photoemission electron microscopy. Very clearly, this shows here X-ray coming in at grazing incidence at resonant edges, and then this releases photoemitted electrons, very basic physics. But the key point that I would like to highlight here is that as opposed to a ferromagnetic case, which involves imaging at the main edge, for example, let's say we have a cobalt coupled to an antiferromagnet that I'm just going to show here in very early team works. The ferromagnetic order can be mapped with circular dichroism. It's a first order process, and therefore we are able to directly map the magnetization. Whereas for an antiferromagnetic system, we now look at a linear polarized X-ray dichroism. And this is a second order process, slightly weaker as compared to the first one. And here we can map the Néel order. This is necessary because the antiferromagnets have almost negligible or absent net magnetization, and therefore we would usually not observe circular dichroism in these systems. As noted in these images here, one key point to observe is that maximal contrast in the ferromagnetic case is between oppositely aligned textures, but in the antiferromagnetic case, it is not possible to distinguish 180 separated domains, but only 90-degree separated domains, and that is why the contrast looks like this. But in this particular work, where they first showed the implementation of some of these ideas, very clearly there's a coupling between ferromagnet and antiferromagnet, and these techniques are very useful, resonant at the particular element edge. Now, in order to actually not only look at the overall structure, but to map the local variations, we do something called the AFM vector mapping. And this really is the brainchild of our very close collaborators at Oxford, Paolo Rodali and his group, where they obtain this by using angle-dependent X-ray polarized linear dichroism, and that is then integrated and fit to actually obtain various orientations of domains in the system. Now, I've very simply shown here three cases because Fe2O3 has a trigonal structure, and predominantly you have three 120-degree separated domains, and they are time-reversed components. And as you can see here, this is obtained by fitting the linear dichroism value as a function of the overall evolution of the angle between the X-ray polarization as well as the local Néel order, which is captured here as phi. And by fitting this simple approximation, we would actually be able to get the local phase of every particular pixel that we're looking at, and thereby reconstruct, in some sense, a vector map of the antiferromagnetic order at the nanoscale dimensions. Now, this was originally developed for TEAM, but our very recent work, which I will very briefly show later on, has allowed us to also translate this to X-ray transmission microscopy as well as X-ray holography in transmission geometries, which allows us much more freedom. So in some sense, this is a very general technique that can be adopted here. Now, the samples themselves are drawn by pulse laser deposition, and this involves the growth of the functional layer on top of a appropriate substrate, such as sapphire in our case, which have very closely aligned structures. They're slightly off in their lattice parameters, which causes a slight strain, but because we grow slightly thicker samples in the order of about 25 to 30 nanometers, all that strain is completely removed, and we actually almost retrieve back to complete normal bulk parameters of Fe2O3. These films are of extremely high quality as measured by as identified by the Laue oscillations, as well as the narrow full width half maximum peaks in the rocking curves. We've also done TM analysis, which has revealed that these are very nicely structured. Now, having all this established, let's actually look at the experimental data, where we now have the modern transition, which I have sort of convinced you about, and we start from the low temperature state, and we're looking at linear vertically polarized stream imaging. And if we look at this image here, we see predominantly it is covered in purple because we are in the low temperature easy axis phase, and therefore purple color corresponds to out of plane orientation. And then there are these walls separating various domains, and evidently these are going to be the antiferromagnetic domain walls in the sample. which are then colored yellow-orange. As we now warm the system towards and across the modern transition, we observe very interesting phenomenology that these domain walls start to firstly widen. And at the same time, there is emergence of lighter regions in the matrix that starts to happen. These lighter regions correspond to the emergence of in-plane domains which are nucleated, which is matching very well with the understanding that the modern transition is a first-order phase transition. Now, as we further warm the system closer and closer and across the transition, we start to see emergence of greater yellow-orange and smaller purple until at the highest temperatures where we have predominantly yellow-orange. But now the curious feature is the fact that there are many purple dots or little bubbles that are actually observed in this image here, which persist all the way up to room temperature far above the modern transition in the sample, which happens to be around 240 Kelvin in these thin films. Now, it is interesting to note that some of these bubbles tend to annihilate with respect to each other at certain temperatures, but certain other bubbles continue to persist until higher temperatures. And then, therefore, this necessitates to understand what are these bubbles, why are there purple objects at the high temperature state? And of course, given our understanding of the Kibble-Zurek transition, we would suspect there to be some kind of topologically non-trivial texture. Now, at the low temperature state, we can now create a detailed in-plane vector map by using the angle-dependent experiment that I suggested earlier. And in the low temperature state, we're able to get these winding domain walls. It is clearly evident that we can see both nail and block textures, which suggests that these are not chiral objects, as expected, because there is no symmetry breaking interaction in this terminal state. At the room temperature state, we now observe a rich mosaic of in-plane domains, many of them consisting of trivial domain walls and some pinch points which actually have a topological structure. Now, in order to convince you that they are topological, it's best to compare the image at the same position between the linear vertical and the angle-dependent linear horizontal images. And here there is clearly one-to-one correspondence that wherever there are these pinch points, that is corresponding out-of-plane bubble regions. So in some sense, as the modern transition has occurred, what has happened is that the out-of-plane region has sort of shrunk and gotten trapped. And because it cannot unwind, it remains as a sort of metastable topological object, persisting until higher temperatures. Now, if we look at individual objects and zoom into some of them, let's start with the bottom one here. We actually have the nail vector pointed out as the white dashes and the R, G, and B colors corresponding to the in-plane phase. Now, note this is modulo 180 because of the fact that this technique cannot distinguish objects which are anti-parallel to each other. So, but irrespective, we can very clearly note that there is some kind of winding, which is actually corresponding to a block AFM meron. Likewise, we have an object which is the nail AFM meron, which is some kind of outward pointing structure. And then we also have the anti-meron, which consists of the opposite winding in comparison to these two objects, which is very clearly shown here, given the diverging kind of structure. So we firstly can identify very straightforwardly the topological charge half entities in the system. Once again, as you notice, I've only given the modulus value of the topological charge, not the absolute value, because we are not able to distinguish the core orientations, and therefore we only know this to a certain modulus value. Now, apart from these individual entities, we can also see various pairs which are present across the sample. Some pairs, I'm just sort of zooming into two of them, which actually are at some little distance or at some extremely close proximity with respect to each other. In some sense, as you can see, this is almost resolution limited as far as this technique goes, which is almost down to 50 nanometers. So these are really tight objects. Now, these pairs could be either an AFM bimeron, as I had mentioned earlier, or it could be a topologically trivial meron pair, depending on what their core orientations are. Of course, unfortunately, we're not able to resolve the core, so we can't tell which is which. But our suspicion when we actually did this work originally was the textures which annihilated could perhaps actually be topologically trivial pairs. In my image here, if I were to just remind you that they annihilated, this could be actually topologically trivial pairs, whereas the ones that survived could be non-trivial. This was our belief at the time, and in order to really understand this and ground it, we are actually doing further work. But nonetheless, we do know that individually these objects are topological of charge value half. Now, in order to convince that this is not a ferromagnetic object, but only an antiferro, we have actually done XMCD contrast, And as expected, these objects do not show any contrast whatsoever. So we know this is coming from antiferromagnetism. Now, having established the basis for this, let's see other ways to actually control the antiferromagnetic topological family. We start off by looking at magnetic field control. Ideally, we are working with an antiferromagnet, so we want some sense of robustness. But I should point out that in the in-plane state, there is a canted moment present here, which actually couples with an external magnetic field via the Zeeman effect, and therefore you would be able to observe very clear hysteresis loops in the sample. And we actually have done some interesting experiments where if we apply slightly smaller fields in the system, actually the density of topological numbers remain the same. Please note that this is actually an ex situ magnetic field experiment, and therefore these images are in remnants. This is quite interesting because it may be possible that some of the ferromagnetic objects may have already annihilated here, but antiferromagnets in Fe2O3 survive. But of course, if you apply extremely large fields where you start to realign significant fractions, you would still land up annihilating some of these textures in Fe2O3. There are, of course, ways to extend this number and shift this anisotropy, which is really a materials engineering term. But what I'm trying to show here is that it is possible to use magnetic field as an annihilating mechanism, but only very strong fields. And if it is then the system is taken below the Morin transition and recycled back at room temperature in absence of any field, we actually recreate the same topological density as compared to what was seen before. This is very important because this shows that this is a reversible process, and this was really important to us because Morin transition is allowing that accessibility, which unfortunately Neal would not allow, which is placed at much higher temperatures. Now, having looked at that, let's look at another control mechanism, which is chemical control. The first set of images that I showed you actually had the transition sitting at 240 Kelvin. While this is good proof of principle, if you want to do realistic use of these textures, it has to be sitting at room temperature or above. And therefore, we investigated how this can be done. This is actually quite straightforward and very well known in the antiferromagnetic in the Fe2O3 community, that by doing doping, you can actually shift the Morin transition either down or up. In the case of rhodium substitution, we delicately tune the effective single ion and magnetic dipolar anisotropy such that the transition now sits at room temperature, and the same phenomenology that we've seen below actually repeats here as well. So it is very possible to actually use this functionally by curating the transition as desired. We then analyze the evolution of the dimensions of these textures, both the domain wall below the Morin transition, and the gray being the Morin transition, and the high temperature actually hosting the topological objects. And I'm just sort of focusing on the relationship here, which discusses how the full width half maximum radii actually scale as a function of exchange and anisotropy by using a very simple linear Miron kind of an ansatz. And we see that the data fits reasonably well. We avoid fitting in the region very close to the transition because that's where the anisotropy goes close to zero, and therefore the size of all textures would diverge. As you saw this in my previous images, this is indeed the case because we actually have a composition of in-plane and out-of-plane domains in this gray region, so we avoid that. But nonetheless, in the high temperature regime, we can actually clearly see that they are declining. Now, by doing rhodium doping, we can completely shift the position of the transition, and therefore we are able to completely redefine where in-plane and out-of-plane textures can be stabilized, and therefore there is unprecedented sort of control over dimensions that can be obtained by doing careful doping. Then we come to a crucial part, which is then interfacial control. All the textures that I showed you so far were actually having platinum overlayer, as I mentioned earlier, but instead it is possible to use a ferromagnetic overlayer. This was actually done previously by the Rodiley group, and what they observed was that any topological textures are actually imprinted onto the ferromagnet by an interfacial exchange mechanism. I'm just zooming into a very small region here to actually show how the RGB texture, which is actually mapped by the same process, corresponds very closely to the arrows. Now, the arrows can be actually used because cobalt is a ferromagnet, and we can use angle-dependent mapping to create these cobalt maps. And if we analyze the value of the XY component, the magnitude of the XY component of the cobalt, we can clearly see that while there is the value remains almost constant away from the cores. As you go approach the core, suddenly the XY components diminish, and because of the preservation of the length of the magnetic moment, it would imply that the cores would actually be out of plane, either up or down. And very clearly, the orientation of the swirling can then be analyzed by the curl of these objects, indicating that ferromagnetic objects are also very clearly topological, and they're coupled to the Fe2O3 case here. The key distinguishing factor between this body of work and the previous one was that here the system was prepared as is, and the presence of the cobalt overlayer enforces a significantly strong in-plane anisotropy, and therefore these samples actually do not necessarily exhibit modern transitions, but they were actually observed right after the work itself. But with platinum, we actually have very systematically tunable and reversible processes that are obtained in the system here. What is key to note is that if the ferromagnetic overlayer can be grown carefully and the antiferromagnetic layer appropriately doped, it may be possible to actually realize a ferromagnet-antiferromagnetic interface, which would still have the modern transition and still recreate all these phenomenologies in a reversible process, which then is very critical for any kind of implementations. And basically, this is purely because of the interfacial exchange. Now, given that we have looked at what is the discovered mechanisms and how we can control it, I would like to sort of spend the last 10-15 minutes discussing about what really lies ahead for this body of work. And I would first like to start off by discussing our very new results in freestanding membranes. And this is actually achieved by having freestanding Fe2O3, which is then transferred and supported on silicon nitride. And this is very critical for us to do any transmission geometry experiments where a substrate is not blocking it. This fundamentally was necessitated because we wanted to do experiments which allow in situ control, and this is not as easily possible in PEAM because of the electron optics that are present in the system here. But if you have X-ray transmission, a lot of in situ experiments can be done. And so this is done by STIXM. And I've just shown a micrograph here of what it looks like. The intricate pattern shown here is actually a heater which is located on the system, and the image that is actually in the background is actually the Fe2O3 membrane, which is placed on top of the silicon nitride silicon holder. Now, this system also hosts a modern transition when doped appropriately, and this is close to room temperature. This was carefully crafted because we wanted to meet the system requirements at the STIXM. And again, what we observe is that as we drive the system from the low temperature domain wall state to the high temperature, we actually retrieve all the topological objects in the system just as before. Now, an interesting feature to note here is that this sample does not have any overlayer. There's no platinum here, and still we are able to observe these textures, which convinces very strongly that platinum is actually not necessary to stabilize any of these objects. This is, of course, not entirely surprising because we know they're emerging because of the Kibble-Zurek equivalent transition. But more importantly, this result actually points to addressing a key gap in these kind of antiferromagnets, because oxides are not necessarily very compatible with silicon nitride because of their growth conditions and so on and so forth. But because they can be grown as membranes and they can be transferred, it could be possible to make these objects eventually silicon compatible and more controllable in the kind of platforms that are usually used for devices. A lot more development is required here, but this is definitely the first step in that direction. Also, it is then possible to do all kind of interesting in situ experiments, but I'll skip that for now. I just wanted to sort of highlight the fact that it's possible to do with membranes. The next question that we were able to address is the question of ultrafast dynamics. This investigation is more theoretical in nature, and I want to revisit the discussion about the Kibble-Zurek phase transition, which I just showed at the beginning of this talk, which was developed by my colleague, Chihao. And the key point to note is that I'm now actually going to run the evolution of these textures across a paramagnet to antiferromagnet phase transition with V1-like symmetry. And we observe, firstly, that a rich body of textures are formed. We also have various topological textures, but as further evolution happens, these textures start to annihilate with respect to each other. And this is a very fascinating behavior. until ultimately all the textures annihilate completely and we remain in a purely in-plane oriented state, which is shown by the almost white color except for some very little noise seen in the system. So this is a very surprising result because it tells us that the topological textures that are created are actually undergoing annihilation when simulated purely by tuning the exchange and the anisotropy effects. Of course, from our experimental data, we know a slightly different version of the Kibble-Zurek transition across the Morin transition allows us to actually have stable objects which are present in the system for very long durations across our experimental time. So there is some kind of gap here, and we suspect this is because of the fact that the terms included in this atomistic calculations do not include aspects which would then enable complete stability. While their dimensionality can be well defined by A and K, perhaps their stability is coming from some other insights, perhaps there is some role of defects here, or the fact that they actually have canting, which is ignored in this very basic set of simulations here. Nonetheless, these simulations provide very interesting insights into the annihilation processes that are occurring in the system here, and I would like to highlight two of them. First, if we were to have two particular objects, as you can see here, they have the same core orientations. One is winding, and the other one is a anti-winding structure. Therefore, this is a topologically trivial Meron pair, as I showed you earlier. And if I simulate the evolution of this object, you can see that the bodies come close together and gradually unwind into an in-plane undulating state. This is not surprising because it is a topologically trivial pair. Now, something very fascinating happens if we start off with a topologically non-trivial pair. As enforced by topology protection, this object should be stable, but of course, something else actually occurs in the system here. As the cores come closer and closer, there is a whole wave emitted at the end of that annihilation process. I'd just like to repeat that again. You can see the cores come close together and it emanates these waves at the end of this process. This was actually already observed in the case of ferromagnetic texture annihilation between vortices and anti-vortices, but this is a very interesting antiferromagnetic analog of that, which now emits antiferromagnetic spin waves which are present in the system here. And when we analyze the kind of dynamics that they exhibit, this is almost in the terahertz regime, and the annihilation of a topologically non-trivial entity results in these explosive emission of spin waves, which can then be used for any number of exciting spin sources, etc., on chip if we were to actually capitalize this. So this is like the first theoretical indication of something like this, and therefore all this is possible with the topological textures that we have been able to stabilize in the system. And all this happens at ultra-fast timescales. Now, another investigation I would like to share is, can we observe novel antiferromagnetic textures beyond the Kibble-Zurek regime in this material system? And that is a work done by my colleague, Jack. This was done now using micromagnetic simulations, not atomistic, because we wanted to add a new term here, which is a symmetry breaking interfacial Delitzsch-Mori interaction. This is some work where we investigated if we start off with various layers of Fe2O3. Now, because it's a micromagnetic approximation, there is a slight inaccuracy here, but this is still good enough for us to actually start the investigation where individual layers are ferromagnetically oriented and adjacent layers are antiferromagnetically oriented. And this allows us to effectively create the layered structure of Fe2O3 and allows us to investigate what would happen if an IDMI is hypothetically added to the structure. Now, we know this is the Morin transition, and if we were to look at the in-plane orientation of the state, we firstly observe that we are able to stabilize uniquely Néel-oriented merons, and the anti-merons now undergo some form of distortion. So if we were to start off with the block meron, it would actually rotate and turn into a Néel meron because of the presence of the IDMI. But a combination of these textures is also possible to stabilize and to create Néel bimerons. Now, if we were to characterize the size of this object as the intercore distance, we can, by varying the exchange and the anisotropy in the system, create a rich phase diagram of what the sizes of these objects could be. And as you can see here, there is a very rich orientation, very rich control over the dimensions that can be obtained, all the way almost until about 100 nanometer kind of length scale. Now, all this is very good because this is still within what we could comprehend in the limits of Kibble-Zurek, but it would be really interesting to see if we can obtain topological textures in the low temperature state, which is really in the kind of textures that the spintronics community is extremely interested in, which is Skermionics, right? Is it possible to then stabilize Neal Skermions in this system? And it turns out that by the combination of AK and D, it is actually possible to realize these Neal Skermions. First and foremost, shown here is one particular example of the phase diagram for a value of the Delaunay-Mori exchange of the value of 1 millijoule per meter square, which is very standard in the spintronics community. And we observed that in the certain regime of A and K accessible in the material parameters, we actually are able to stabilize antiferromagnetic Skermions. And then if we go to an extremely, the higher end of this regime, we are able to not stabilize them in the sense that these Skermions shrink and they vanish to zero. So as shown here, the sizes of these objects are much smaller as compared to bimerons, going all the way down to about 30 nanometers. This is, of course, limited by the micromagnetic approximation. So we expect that by appropriate scaling, this number can even go down further in the system. And by tuning the strength of the exchange value, you can see here very clearly that we are able to tune the lowest sizes of these textures. So this is something very promising that lies ahead for discovery in this ferromagnetic system. Of course, the question is how are we going to get this IDMI, and there has to be very careful sort of control over the interfacial interactions then to stabilize these textures. To just give you a slight estimate, this range of stability for a set of standard values of exchange that we use in the system, let's say about in the window of about 14 picojoule per meter, we actually have a wide temperature window where the anisotropy is tuned below the modern transition. And this, depending on the A value, can be tuned in a wide range of parameters, almost up to 20 to 40 Kelvin, which is not which is a sizable range of window to actually stabilize these objects. And therefore, there's some interesting results awaiting in the future. Lastly, I would like to discuss about a possibility of controlling the magnetic topological family by reversible control processes, given the fact that Fe2O3 actually hosts rich correlations between various orders. So first and foremost, I would like to go back to the chemical doping aspect, where we used rhodium doping to completely shift the transition. While this was exciting, this is a slightly limiting process because it is an irreversible transition. Once you make a certain amount of rhodium doped Fe2O3, it is going to remain in that state. What is interesting then is to explore reversible chemical control, and we realize this by doing ionic hydrogenic doping in the system. What is shown here is again the pristine samples, and we now perform hydrogenic dopant by using a process called catalytic spillover. This is a very proof of principle approach. So as you can see here, this is still by using gas atmosphere controls, but it provides some very interesting insights that I will just be discussing now. So we actually have these hydrogen, which is then broken down into nascent individual molecules, and that enters the Fe2O3 state to then fundamentally tune the properties. Firstly, by insertion of hydrogen, we completely suppress the modern transition. So as you can see, this does the opposite effect of what rhodium does. And because hydrogen is a light ion, we can actually perform oxygen or argon annealing, and we can actually remove the hydrogen from the system and retrieve the original state and to recreate the transition. So if you were to sit below the transition in the system here, you would effectively drive a complete reversal, a maximal reversal of the Néel order parameter in the system by inserting and then removing hydrogen. I would like to quickly discuss the underlying physics because it has important implications for future studies. So we observed that apart from various other factors, the key factor that is changed by hydrogenic doping is really the electronic structure. And to convince you of that, I'm showing you here the K edge of the ion in these samples, predominantly focusing at the main rising edge in the system here. Now, what we observe is that in comparison to the pristine state, when we put hydrogen, there is actually a shift towards lower binding energies in the system, which actually then suggests that hydrogen is resulting in some form of electronic doping And this occurs because the hydrogen tends to form bonds with oxygen preferentially, and this therefore weakens the oxygen ion bond, therefore shifting some kind of electrons back to the cations. We can do this quite quantitatively as well, where we compare the shifts with respect to the hydrogen dopant concentration, and we actually find that there is some reasonable correspondence. And when we perform these experiments in control environments in the absence of hydrogen, any of these shifts are completely absent. So the key point here is that although we are using ions to drive the changes, it is really an electronic effect which is driving this process, which is very exciting for controlling and tuning this process. So because of the delicate coupling between the charge and the spin or the parameters, we are able to drive this transition. And this fundamentally comes because of the following argument. So shown here are the two single ion and magnetic dipolar terms, one favoring out of plane, one favoring in plane orientations, and the total K, the total anisotropy, basically follows this evolution here, going from a positive value to a negative, which as we know corresponds to a out of plane to in plane transition. Now, when hydrogen is added, there is a slight shift towards Fe2+, which effectively changes the fraction from a 3d5 dominant state to a 3d5 dominant plus a small fraction of 3d6 states. And this makes all the difference here. Firstly, because of the fact that it is now not completely uncompensated, the effective magnetization in the system weakens, and therefore the magnetic dipolar interaction weakens. But at the same time, the spherical symmetry of the 3d5 is now significantly reduced, and therefore the spin-orbit coupling becomes much stronger in an Fe2+ state, which then enforces the presence of a strong single ion contribution. For very specific technical reasons, it turns out that this is a negative value, and therefore effectively the single ion suppresses much more in the magnetic dipolar part, and therefore by tuning hydrogen, we're effectively able to go from a positive negative transition to a completely negative remaining state, which then drives the annihilation of the model transition in the system. And because this is reversible, you can go from green to red and red to green again, and so on and so forth. So this is very interesting because this hydrogenic process, while we have actually shown this only as a proof of principle, there are very nice body of work by Jeff Beach's group, for example, where they drive hydrogenic control of cobalt metal into oxide and metallic state by using some form of proton pumps. This can, of course, also be done with lithium, and therefore these processes in principle can be controlled via fields. It is entirely imaginable that without actually having hydrogen, but only using electrons injecting in and out of the system, this is also possible, which is extremely promising for electric field control. The next is, of course, electrical current control, and this is by using spin Hall effect based spin torques, where the use of heavy metal layer is now allowing us to convert charge current into spin current, which can then be injected into the magnetic layer. Very excellent reviews have been written on the subject, particularly by Hariom and his colleagues, and also how this can be used to drive antiferromagnetic order are some very interesting results here. Firstly, of course, this was demonstrated in platinum nickel oxide, where the heavy metal is then used to inject some form of spin currents into the system. And they were able to observe the changing of the local order. And this is done by Matthias Flaui's group, and also by other groups such as Yishao Lu, as well as Ralph Young's group, where they have been able to realize this in platinum Fe2O3. So while all these studies actually are referring to electrical control of non-topological antiferromagnetic states, it is in principle completely possible to exploit the platinum Fe2O3 interface, then to inject spins into the Fe2O3 and thereby drive ultra-fast dynamics. As I discussed earlier, Fe2O3 has ultra-low Gilbert damping. This would then enable fast motion of topological textures approaching kilometers per second, which would then allow us to break into very fast control of topological textures. So with that, I would like to quickly highlight our very recent mini review that we have written. This is out on arXiv now, which actually discusses various topological textures and how these are controlled in correlated oxides, in particular, the Kibble-Zurek transition, which I just discussed today, and various others, which are already very well known in the community from before. And with that, I would like to sort of highlight the key takeaways. Firstly, I hope I've convinced you that Fe2O3 is a promising platform to investigate AFM Skermionics. We are not only able to utilize the Kibble-Zurek transition to create and destroy textures, but we also have unprecedented control over their dimensions. We have been able to achieve freestanding membranes, and we are able to imagine a possibility where they can be transferred, although much more work needs to happen in that direction. The physics in the terahertz regime can actually be unlocked, and the key factor that will distinguish all these developments is also the addition of IDMI, which will actually enable a completely homochiral AFM family, which is a necessary step for us before we start discussing about electrical current as well as field control, which would then allow us to really move towards actual devices from the scientific concepts that I've just outlined today. With that, I would like to really thank my supervisor and my colleagues at National University of Singapore, as well as our very strong collaborators in Oxford, Prof. Paolo, and my entire team and collaborators there. The support of our X-ray experiment beamline scientists, as well as various other teams across the world. And with that, I'm very happy to take any questions. Thank you.
Thank you very much for this interesting talk. Do we have questions? So please write them into the chat, or you can raise your hand. So I see two attendees raising their hands. So the first one is Thomas Mercheli. So please turn on your microphone.
Thank you. So I was wondering, in Kibble-Zurek, quench rate is an important parameter which determines density of the defects. So have you been trying this, and what are the results?
That's a very interesting question. Actually, we are very well aware that the quench rate affects the density of topological objects. This is actually an experiment that we have tried. And within the range of tunability that we could achieve, going from ultra slow, effectively almost quasi-static transitions, which is the kind of images that I've shown here, to slightly faster ones, we have actually not observed significant change of the density. That said, I must highlight that the kind of in situ transitions that we can achieve in the system are limited because of what is possible incompatible, which is compatible with the heaters, etc., in the synchrotron. So this is slightly limited, but I do think that there are some very interesting questions that could still be asked and investigated because of the ultra-fast quenches. But in the range that we have investigated, we have actually not seen significant changes in the number density, which I must admit is a narrow range.
Thank you.
Thank you. So the next question is from Igor Sandalov, and I'm trying to allow him to talk. Yeah, please.
Okay, thank you. I have a couple of questions. One concerns experimental part and another atomic simulations. As for experimental, when you using this term zooming image certain regions, then what do you mean from experimental point of view? How you can control, yes, exactly, directions of spins and so on. So where it comes from?
I am not sure if I've understood that question correctly, but I guess you're asking what allows us to image these specific orientations?
Yeah, well, what experimental technique is using for this zooming?
Okay. No, there is no zooming in here. This is actually the same image. I've just blown it up here. There is no specific zoom in here. This is the same resolution of the actual experimental data. Every pixel size corresponds to 20 nanometers, but the real resolution of textures is on the order of about 50 nanometers. So what I've just done is I've just blown it up, but it's really just the same data.
Okay, so actually all these directions of spins which you are drawing, it's a kind of guess.
No, that is not a guess, right? So that is exactly the technique that I was sort of indicating here. What we actually do is that we perform linear horizontal imaging of the entire area at one shot, and then we rotate the sample one by one, and then we collect various phase values phi relative between the X-ray polarization and the sample angle, which then allows us to actually construct variation of the dichroism across the entire image. Due to the variation of the dichroism, it is then actually possible to fit this data pixel by pixel, the contrast, and that allows us to assign a unique value of the antiferromagnetic phase. So that fitting process then allows us to actually attribute a value of RGB, which then corresponds to the orientations which are shown as per the color wheel here. Maybe this is a slightly bigger image here. So as you can see here, because this assignment is guided by the fact that there is trigonal symmetry, and therefore there are predominantly 3 domains which are separated by 120 degrees and their counterparts. So you actually have this 6-fold distribution of 360 degrees, which is actually shown here.
Okay, beautiful. But if you take another sample, then the location of all these things will be different, right?
Absolutely, because there is nothing fixed by the technique itself or the growth process itself. The Kibble-Zurek transition is a probabilistic process, and therefore the place where these would be nucleated are probabilistic. So our intention here to use this transition was actually to show that the system is topologically rich. However, if we want to exploit it experimentally for racetracks, it would be actually important to use other techniques which are athermal to guide the stabilization of these textures.
Okay, actually,
Thank you.
I was
So the
asking...
next question is from Gisela Schütz.
Can you hear me?
Yes.
Thanks for this very fascinating talk. I have a similar question. All these pictures of these domain structures, therefore you need a synchrotron. If you look, or if you think in terms of devices, you cannot characterize any system with the synchrotron. It's too much work. And all antiferromagnetic domains I have seen so far are extremely out of control. So you always say about topology, it is a control, but the fact is that you have here extremely irregular structure with some kind of structures which look like antiferromagnetic topological systems. I cannot see the reason for this topology, and also, is there an idea how to control the domain in any case? I think this is not possible, even not with a ferromagnetic layer via exchange bias or so on. And related, can you have any access to these structures in the lab, maybe by nitrogen vacancy microscopy, but this is all extremely large effort.
So thank you, Gisela, for the question. I think what you are trying to ask is, and correct me if I'm wrong, how is it possible to actually image these in a lab setting, and which would be necessary to actually use them for devices? Is that right?
Yeah, and you need for the device, you need a control of the domain structure, which is not possible up to now for any antiferromagnetic system, as far as I know.
Okay, so I would like to perhaps answer that question into 2 parts. Firstly, regarding the control of textures, one thing I would like to highlight is that if the system, as I have suggested here, contains sufficiently rich U1-like symmetry, it is firstly possible to stabilize topological textures of charge half. That's first. Now, it is entirely true that the background of this is a mosaic, trivial domain wall structures, and this restricts the direct implementation of what I've shown you here, which is exactly the reason why I sort of suggested the discussions in the later part of my talk here, which show that we are able to create textures both in the in-plane state as well as in the out-of-plane state in a controlled manner once we have IDMI. This, of course, begs the question, how are you going to do this experimentally? And of course, the appropriate way to realize this is by using fine interfacial control, which is something that we're currently developing. And once we are able to do that, it is possible to create unique textures in a uniform background purely by doing spin injection with, from the perpendicular direction. So it is in principle possible to recreate the same phenomenology of processes that is known in the ferromagnetic community in the antiferromagnet. Then comes the question of how do you detect them, how do you read them, and ultimately all this has to be done electrically. I feel these are extremely legitimate questions, and these are important questions for us to address. One important way to do this in a lab setting in the absence of the synchrotron is by something called nitrogen vacancy imaging. This is something that we have already applied on our samples, and we actually are able to see topological textures even with NV imaging. I've not shown that data today for brevity, but it is entirely possible to do this in the lab setting. That's first. And how do we do this electrically? It is very clear to me that the electrical control is going to be possible by spin-orbit torque control via spin Hall effect, as is done in the ferromagnetic community. But the question of how this can be read out electrically, I feel that further development needs to happen. Some directions already with spin Hall magnetoresistance are present, but these are slightly weak effects. So it remains to be seen how we can do this electrically. But I feel we are really at the birth stage of this field. Some of the results that I've shown you are the first in this community, so we have a long journey to go. And hopefully over the next few iterations, we will be able to answer all.
So thank you.
Thank you. So the next question is from Vaida Wu.
Hi. Thanks for the nice talk. I have two questions, if I may. One is more related to this Kibble-Zurek mechanism. As you show, the Kibble-Zurek mechanism is from second order phase transition, right? So it's describing quench through the second order phase transition, and the line you draw, right, is divergent of the correlation length at the transitions. But this Morin transition, as you also show, right, is a first order transition. So seems to be a little bit disconnect, because the way we describe first order is like, you know, the nucleation and domain growth, right, as you also show in your image. So there's a little bit of a difference, right? So I mean, I don't know, how can you make the connection between them? Yeah, this is my first question. And second question, maybe we can relate it to the image. And so after the Morin transition, right, in the room temperature, in addition to those topological whatever marron, right, dot you see, there's also some texture in the background, right? So what are they, and whether they related to the domain in the lower temperature or not? I mean, that's maybe the two questions I have. Thanks.
Thank you for those questions. So you're absolutely right. The Kibble-Zurek originally was proposed for second order phase transitions. And what we have actually shown here is across a nucleation-driven phase transition. So there is a clear disconnect between what is the theoretical motivation and what we have actually done experimentally. And this is very interesting for us because in my knowledge, at least, I don't think previous investigations across a first order transition have resulted in topological defects, and we have been able to actually address that question. So we feel that significant amount of physics that is existing here purely because of topological arguments can again be translated across the first order, although the dynamics of the topological defect nucleation, etc., very well known. And I think one of the previous audience members also asked that question. It is not clear how that translates across a first order phase transition. So if you were to, for example, change the quench rate across a Morin transition, would that then scale in a certain manner in a power law or a logarithmic law as a function of the number of topological defects? That does not necessarily translate directly from the second order nature. And this is something that has to be investigated both experimentally and theoretically. So this is really an open question. The second question regarding the kind of textures that we are seeing in the background in the neighborhood of these objects. As you can see here, the pinch points indicated either as circles or squares are topological centers, but the background is actually consisting of trivial domains. So you can see here that...
Sorry, excuse me, actually it's the previous slide in the image. This image in the 300 Kelvin, right? You see this, you're measuring, in some sense, the outer plane Néel order, right, in this image?
No. We are able to look at various orientations of the Néel order. The polarization of the X-ray is vertical, but we can actually distinguish the in-plane from the out-of-plane because they produce different contrasts when you use a vertically polarized X-ray. So as a consequence, you would actually have the core objects which are having a certain color which match with the same color orientation as the low temperature state because they are both out of plane. Whereas the background would match because it's in plane with the domain walls of the low temperature state. So that is basically how we can clearly convince ourselves that they are of very different magnetic orientations. But we have done much more exhaustive mathematical analysis also to convince what are the various permutation combinations in the system, and all of that can be very clearly distinguished with the polarization. But of course, if you want to really resolve the orientation of the in-plane textures, the way to do that is by using the vector mapping technique, which I've mentioned before, which then actually reveals there's a rich mosaic of structures.
Okay, thank you.
Thank you very much. We might have another question from Igor Sandalov. Do you have another question?
Another question was about atomic simulation. Probably they used some fluctuations, and what kind of fluctuations? I am afraid that the result should depend on type of correlation functions used for fluctuations and so on. Is it like that?
That's a very interesting question. So if I just were to skip to that, we have actually done a very simple version of the Kibble-Zurek transition, which involves the starting of the state from a paramagnetic orientation and stabilizing the ground state of the system to be in the in-plane state, which actually hosts the U1-like symmetry. And that is itself sufficient to recreate the magnetic topology that I've mentioned. It is entirely important for us to actually investigate this by controlling the thermal noise, etc., and the correlation functions, as you mentioned, between various spins, both in space and time. But that level of sophistication has actually not been used yet. Even with a very simple model, we're actually able to recreate the kind of topology that is known to exist with the Kibble-Zurek transition.
Okay, thank you.
Thank you very much. Vaida Wu, do you have another question?
No, sorry, I forgot to lower my head. Sorry.
Maybe I have a final question. You have shown these antiferromagnetic merons and antimerons, and they occur kind of in pairs. So do you have any way to measure the distance or the strength between them? So how much they are bound to each other, or how much it gets towards like a liquid state?
That's a very interesting question. So we have actually tried to do pair correlation analysis of this, but unfortunately we found that the amount of defect density that we have does not provide sufficient statistics. But it is very straightforwardly possible to image, for example, in some of these cases, the intermeron distance. And we still feel that they are sufficiently sparse at the moment, but there is very clearly presence of some kind of binding between them. As you can see here, a meron-antimeron pair of this kind would actually involve some form of a domain wall, and the lowest length to which you can compress these objects and still have them stable is going to be determined by the energetics of the system. In some sense, this is also evident in some of the simulations that we've done. I think this one here. So, for example, the intermeron core, written here as SQ, actually can be mapped and evolved as a function of the exchange as well as the anisotropy, and we can actually have a very rich phase diagram where they are effectively very far away from each other, that they behave almost as independent entities, and then in the upper right corner here they come very close to each other, and therefore they behave almost as if they are coupled to each other. And we ideally want to be in the smaller regime so that we can control them for textures for any kind of systematic use.
Thank you very much. So thank you for your talk, and thank you for taking the time to answer the questions. In total, we were about 100 people. So see you all again next week. And with the